Hello, my name is Ryley Bresee, and I am going to give you a presentation about what I did for my final project for my flight simulation class at Utah State University. For the class, we had to build a basic flight simulator, so we coded in all the physics equations, used an RK4 integrator to propagate the simulator forward in time, and then we had to develop a final project. We had to add some additional functionality. I chose to do some controllers onto my simulator, so I did a airspeed, an altitude, and a roll rate controller. Basically, I want to go through just a little bit of introduction to my project, some of the control techniques and assumptions I used, the airspeed controller development, the altitude controller development, the rates controller development, a demonstration so that you can see my actual simulator working, the response plots from my simulator, and then a little bit on the lessons learned and future work. Here is what my simulator looks like when you open it up. On the left over here you can see are just some of the states, the commanded values, the inputs to the system like the throttle, the elevator. On the right there are also states, the angle of attack, side slip, the rates, and all those things so that the pilot can see what the current state of the aircraft is. Some of the control techniques and assumptions that I used. So I used classical control theory, not state space. Basically this means adding poles and zeros to add controller gains, and not setting up like a matrix of state space, basically of that. So basically I stayed linear time invariant, so that means I need to assume I'm operating around a specific operating point that is close to my states, and so I basically linearize the system around the initial airspeed that is given, and so that is around 175 feet per second, and also level steady flight. And so as long as I'm not going super fast or rolling really fast or changing my attitude very quickly, then my controllers should be able to handle that. I also use single input, single output SISO controllers. Just to simplify things, I used continuous time controllers as well, even though I'm using an integrator, an RK4 integrator to propagate. And so technically it's a discrete system, but I just assumed as long as I used a small enough time step that it would be like a continuous time controller. I also used Control System Designer with Matlab to design the controllers, and that is a picture of it over here on the right. Control System Designer. I used open and closed loop Bode plots, step response plots, and a Matlab script to develop my gains. I did proportional controllers for all my controllers just to simplify things as well. Here, the airspeed controller development I'm going to go through in detail, then the other two I will not go in as much detail. So in order to do a controller, you start with the equations of motion. For the airspeed, I am concerned with the u dot equation because u is my x velocity. So here I just want to decouple my system. Right now I have v and w in my system, which are not u. And so that's bad because that couples my system to the v and w axes. So my airspeed is coupled with v and w. It's also coupled with r and q, which are not my u direction. R and q are rates, so angular velocities, and q is my pitch rate, r is my yaw rate. Those are not in the x direction, so that also is a coupling. I just neglected those because I assumed that r and q were going to be small. Next, bubbling down, I'm assuming that alpha is going to be small, and so I can just use v instead of and V and U interchangeably. Next, I'm going to assume that theta is small. That's the elevation angle, so that's how high I'm pointed above the horizon, how much I'm climbing. I'm going to assume that's small, so that just turns into a theta, but also it can be neglected because it is so small. Next, I need to find, so that gives me u dot equals g over v times t plus x. I need to find an expression for t plus x, so I go to my aerodynamic model, which you can see over here on the right hand side. So this part is my aerodynamic model that I'm using. I'm going to assume that beta and alpha are small, which they're going to drop out. Then u over v is approximately 1 because I made that small angle assumption, my small alpha assumption. So that's going to be approximately 1, which just leaves me now boiled down to this equation. Now I need to split tau up into a more usable form, so I'm going to have a delta tau plus tau ref. Tau ref is at my trim condition, which is going to basically cancel out my trim drag. So those two, tau ref and my trim drag with all this stuff, cancel each other out. So now I'm left with delta tau, which is my input to the airspeed controller system. Now I want to take that equation and go a little bit further. I want to go into use the Laplace transform and go to the frequency domain. U dot is a derivative. Anytime you have a derivative, it equals an S. So I would have S times U of S, but I actually divided that over, which is why I have the 1 over S. This is my frequency domain transfer function. Now, if I go to block diagram form, I have the plant, which is basically the 1 over S times all that stuff. So here's my plant. Then I have my controller, which is basically my delta tau and any fancy stuff I add into there. Because the system is discrete, I'm going to add a time delay, which even though I'm modeling it as a continuous time system, this time delay will help me approximate it better. Then I used Matlab script and control system designer with Bode plots to develop the system. One thing to keep in mind is that the Nyquist frequency, which is 1/2 the sampling rate, was 25 Hertz. I wanted to keep the bandwidth below the Nyquist frequency, and so generally a rule of thumb is to divide that by 10, take it a decade lower. So I tried to keep all the frequencies below 2.5 Hertz, or the bandwidth. I tried to keep the bandwidth below that. Here is the open loop Bode plot for the system. I have 82.7 degrees of phase margin and 21.8 degrees of gain margin with this gain, so 0.42679. That is pretty generous. I did it generous because, again, I was trying to keep the bandwidth below 2.5 Hertz. And so in order to do that, I just have really large gain and phase margins. That was the airspeed setup. Now the altitude controller, as I said, I'm not going to go in as much detail. Basically, I have the transfer functions over here on the left, and then I have the block diagram form here on the right. It's a 3 cascaded loop. In order to use proportional gains for all of them, I had to do it this way, which allows me to simplify the controller development while still maintaining stability. Now the altitude controller here is the actual implementation. This is the code that I implemented. You can see it's fairly simple. It has a few if statements to account for the saturations in the system, but other than that, it's fairly straightforward, just putting the gains in that I came up with. And then over here on the left is some of the responses, so like the step response to the system. These are not going to be exact because I have a discrete system, but I'm modeling it as a continuous system, so these are not going to match up exactly. The rates controller development, here on the left you can see the transfer function I used in the block diagram. Again, just a simple proportional controller. Here is the actual code implementation, so very simple because it's just one loop and it's a gain. Now I want to demonstrate my simulator, not that. demonstrate my simulator. And here we are going to see how these controllers act. So this simulator was developed in Python. Everything, the graphics, the integrators, all of that was developed in Python. And when it pulls up, we can get going and show you the 3 controllers that I have on it. Okay, so as you can see here on the left are all the states, as well as on the right. If I hit spacebar, I can see the aircraft. It's just keyboard inputs to control it. Right now, the throttle, so the airspeed command, or the airspeed controller is always on. So if I pitch up, you should expect to see that the throttle jumps up. If I pitch back down, you can see that it's not. Now the elevation angle shows me my orientation. So right now I'm about level. If I go up to, say, 10 degrees of elevation angle, you can see my throttle is now at 60% to maintain that airspeed. The airspeed is not going to hold exactly because it's a proportional controller, and it never will drive the error exactly to 0. And over here you can see the airspeed error. So that's that one. Now if I want to do the altitude controller, right now it's turned off, but if I hit K, it will turn it on. Sometimes it takes a couple hits to get it to turn on. So there you can see my error. I overshot. Now I'm undershooting a little, but basically it will settle back down. Even if now if I turn, it will still try to hold the altitude at the commanded altitude. So here you can see the actual altitude, here you can see the commanded altitude, and it will try and hold those the same. And those of you that know much about flying, when you bank, you basically induce a side slip and you lose altitude. And so, as you can see, it's trying to keep it the same. Now, if I were to turn this off, now it's off. You can see I'm just slipping all the way down. If I turn it back on, you can see that it's holding it much better. So it actually is doing a lot. It is holding it steady in this turn. Now, the last one is the rates. If I hit L, that turns the rates on. Basically, I have a few keyboard things to turn the rates. Basically, I wanted something that would just roll me at a constant rate. So there you can see I'm rolling at about 16. I can roll back. A couple other keys make it roll a little bit slower. And again, it's not perfectly constant because I'm using a proportional controller. So that's my simulator. Just wanted to look at a few more slides here, just showing the response. So just some ramp responses. You can see that it tracks it fairly well. The error does get a little bit larger, but it's still tracking fairly well. Here's a step response for the airspeed controller. I basically flew it at a very high elevation angle to get it to slow down, and then leveled off to see this step response type of a behavior. The altitude controller, this is it responding to a ramp. So it responds, it does kind of track the ramp. It has a little bit of phase lag in it, but it does catch up and start tracking it better. It never actually zeroes in on the error because it's a proportional controller, but it will track the ramp. Here's a step response for the altitude controller, and as you can see, I had the controller turned off, ramped up the commanded value to something different than the actual current value, then I turned it on and was able to see the step response. Then I did it once more, turned it on to see the step response. Now I just wanted to conclude, basically some lessons learned. As I went through this, I was able to understand that proportional controllers actually do work fairly well. Although they won't ever drive the error in your system to 0, they do work. And also using that 3 cascaded loop system. I haven't done a 3 cascaded. I've done a inner and outer loop system before, but the 3 cascaded system was something new. That was really fun to work on, and because I was able to do that, I was able to simplify the controllers significantly. I do want to go back and work on implementing some other controllers. Probably a lead with an integrator would be the next one that I would implement on these systems, and see if that will help drive the error down to 0 faster. Thanks for watching, and I hope this is helpful for you, and goodbye.